All right, if you guys are here to listen to Anthony Bly talk about pH and how we can manage that with a soil health system, you're in the right room. So Anthony Bly, he has had an extensive career with South Dakota State University Extension. He's a soil field specialist. He's had a lot of experience with soil fertility and fertilizer recommendations for different crops. And he's been a huge advocate for soil health systems and conservation in the state. He's long-term no-tiller, probably been no-tilling longer than I've been alive. He's my neighbor, and so I got to thank Anthony for me getting into this kind of a system of farming. So Anthony's a really good mentor. Ask him any questions. If he doesn't know, he'll find it for you.
Thanks, Austin. Wow. Where's that handheld mic?
Oh, hey,
Right
you
there.
gotta have this.
Yep.
Thanks for reminding me.
No, you're good.
And you got the clicker?
You're good. Yeah, we're good. Yeah, now I just have to figure out where to stand. Right here. Okay. Yeah, thanks, Austin. That's humbling. That's really humbling. Appreciate it. Anyway, I get a lot of questions about soil pH, and they're generally about pH being too low. And the question I got to come and speak today was about the concern about pHs being too high. So I have a bunch of slides, and that discussion's at the end, but we're going to roll right through this, and then I'm going to relate it back to soil health and some management things that you can do and think about. And it's all interrelated. All of that you've heard up till now is what it is, okay? But we're going to try to tie it together and bring it together. So what is pH? It's a soil health indicator. It's the negative log of the hydrogen ion concentration in the soil. That's the technical part of it. So really, what does that mean? And so I have that here in the bottom sentence. It's the power of hydrogen. Okay, that's what the little p is. And it's the negative log transformation of hydrogen ion concentration in the soil, to put that very technically. Okay? And some of you probably like, oh, what do I need to know that? But there's a meaning behind all this. You heard Keith talk about the photosynthesis and the carbon. There's a deeper knowledge there. So at all of these things, all of these topics, there's a need to have a deeper knowledge, okay? Just not a superficial understanding. So we're going to go kind of fast, but water is H2O. Pure water has equal concentrations of hydrogen and hydroxide. It will not conduct electricity, okay? It will not conduct electricity. A lot of people think all water can do it, and it won't, because it's balanced. A strong acid like battery acid has 100 million times more hydrogen than a strong base. The logarithmic scale was created for easier understanding. pH 1, pH 2, pH 3, right? The scale ranges from 0 to 14. Okay, all those zeros have been removed. And it's just a lot easier to use. Here's the scale right here. You can see that this is 10 to the minus 14th and vice versa. There's your pH scale. Here's some typical things. Battery acid at the top being a strong or have a low pH. To sodium hydroxide, household bleach, ammonia, they have very high pHs. Human blood is pretty neutral. Okay, pretty neutral. Black coffee is acidic. Milk, is neutral as well. How is it measured? You use a hydrogen ion selective probe, and that's what you see there in the beaker. It's designed to measure hydrogen. It selects for that. In soil, we use equal parts of water and soil. We mix that up, stick that probe in there, measure pH. In buffer pH, we add some sort of buffer to it. You may have heard of Sakura, SMP, Woodruff. What that does is that's a weak salt solution, and that encourages other minerals to dissolve. And so the buffer pH is a measurement of which direction is the soil going. Is it getting more acidic or is it getting more alkaline or basic? Most all of our glaciated soils in this area, the buffer pH will always be higher than the water pH. That's just the way it is. If you get one that's flipped, there's probably a problem with the test. Okay, let's look at the soil colloid here, the clay humus complex. I've got that in the middle. Well, Lemke, I stole it from whoever that is right there. We have those cations floating around in solution, and then we have cations absorbed or held by that clay humus complex. And the ratio of those which are absorbed versus in solution is the same. Okay, so there's the same amount in solution as there is stuck to that colloid. Now remember, the colloid, the broken edges of the clay, the organic matter, they have negative charged surface areas. And so these positively charged cations are held to that. Okay, so that depicts that. And then we look at the lysotropic series here. We have aluminum is held the most tightly to that exchange site, followed by hydrogen, then calcium, magnesium, potassium, which is equal to ammonium, and then sodium is the least held because it's such a big ion. But notice that these are acidic and those are considered alkaline. So why is pH so important? Why do we even care about pH? Because it really affects the nutrient availability to the plant. And you've probably all seen this famous chart. Yeah, it does work here. Nitrogen is available across a wide range. There's a dip here for phosphorus at about 8.5, and it becomes more available as you get down in that 6 range. Potassium's kind of not affected, sulfur, so forth, on down the line. So it does matter, and I have some data later that will prove this point out pretty clearly. So how do soils become basic? Why do they have a high pH? Why do they have a high pH? This is the Ethan soil series right here. These white concretions are lime, and that's free lime in the soil profile. Okay, the prairie developed. Organic acids were slowly released over time and helped dissolve that calcium carbonate that was in the surface, and water took it down deeper in the profile. So where that carbonate exists is really indicative of the soil development. And if you're farming where I farm, some of this calcium carbonate is right at the surface. You can look down and see it because we've had massive amounts of erosion that have taken the topsoil off. Okay? So anyway, so we can also change or increase soil pH by adding lime, which is calcium carbonate, calcium oxide, calcium hydroxide. Wood ashes have a very high pH effect, a liming effect. Some gardeners use wood ash to adjust pH. Or the most popular thing in South Dakota right now is the lime byproduct from water treatment facilities, because that's all we have. We don't have an active lime mine in the state of South Dakota. There were some down in Yankton County, down in that area, some small low-grade areas where they could dig out of the side of the hill and get something that resembled lime, but it wasn't very good quality. There's also some seams in the Menno-Freeman area, very thin, low-grade quality. I think they're kind of trying to use that, but that's how we get high pH. The high pH, the alkalinity in the soil is really a gift. I'd rather have soils with higher pH than low pH. And it's because of this right here. Our very low acidic soils in the tropics have very bad aluminum problems. And we haven't seen that in South Dakota yet. We haven't seen those aluminum problems. So all the acidity in South Dakota is coming from the hydrogen. So these glaciated soils are typically neutral to alkaline. I apologize. My way some of my things are appearing have been messed up by some form of a different PowerPoint version or something. I can't explain that, but we'll get by. So soil pH by depth, you see here in the right-hand column, this is the Brookings soil series here. We can see in the surface that we don't have any of that lime until we get about here, just over 2 feet deep, it starts to show up. And you can see that here as well. We've got a lowered pH in the soil, 0 to 6 inch, because of probably some factors I'll get into. And then we see the effect of that residual or that legacy lime that's been in the soil right here. Okay, let's talk a little bit about saline and sodic soil development. This is my artwork. Anyway, it's my freehand drawing. This thick black line is the soil surface, if you will. So here we go down a little bit into a little swale right here. And we see in the soil that we have the glacial till layer, probably maybe follows this yellow line. And we have a salt accumulation zone, maybe here like this, outlined by the 2 black lines. You can see here it's getting a little closer to the soil surface right here. And then we have water table indicative of these blue lines coming up. And precipitation here falling on the soil. It's falling all over, but our increased precipitation has brought the water table up, and where we've seen the problem with salts are right in this area first. Because those salts have come up they're closer to the soil surface. Where they're further away from the soil surface, where they're deeper, we don't see that problem at the soil surface yet. And we also have some below ground flows of water coming into this area. And so that water that's evaporating is carrying those salts. We call them salts, but alkalinity is another term for that. And we see accumulations of salts here in the basin, but the ring, this depicts the ring around the basin is where the highest salt problems are. That's where you'll find the highest pH. Remember I said this is the alkalinity part right here. Those are what's coming in there and raising the pH of those areas. So I wanted to show you a little bit, going back to that soil colloid, the clay and humus structure. It's just that sphere there, that black sphere. It's not, there's electron microscope pictures of this stuff that are really cool, but for simplicity I just did this. And so I've got the different colors of cations here, the potassium, calcium, magnesium, and then there's a hydrogen, okay? There's some acidity, here's some acidity right there. And then we have the sulfate. The negatively charged ions are not attracted to the soil colloid, okay? They're just floating around out in solution and can move with the water. So if the root's taking the water, it'll go to the root. If the water is going through the soil, it'll take them with them. We call that leaching, okay? So if we have a saline sodic soil, we've got more sodium, that's the yellow, okay? You notice that there's a little bit of sodium over here on the normal soil. There's always a little sodium out there. Most every soil test will pick some up. But in the sodic soil, we have more sodium, and we have more salinity, more calcium, magnesium, potassium, and so forth. But we also have more of the anion for each one of those. So the chlorides, the sulfates, the nitrates, carbonates, they're all out there as well, and that's how we get our saline sodic soil. So just a little depiction of that. But it's the hydrogen that is controlling the pH in these areas. And so you don't see any here, okay? It's high pH. It's high pH. So how does the soil become acidic? Well, it gets there because of soil weathering, leaching, organic acids produced by plant growth over time. They contribute to that process, but the largest one has come from our use of nitrogen fertilizers. Okay? Leftover nitrate has got levels of hydrogen ions in the soil because of the nitrogen mineralization process. There's a hydrogen there, okay? And so those hydrogens haven't been modified by plant uptake. When the plant takes up nitrate, it releases a hydroxide, and the hydroxide neutralizes the acid. So if we're applying too much nitrogen fertilizer over our yield goal, year after year after year, we're slowly acidifying our soils. So it's very important not to do that. I got some data to prove that as well, or to show you that. So here's the nitrification process. Starting out with ammonium and oxygen, we have those two acids, those two hydrogens, we have nitrate and water. So those are the acids produced when ammonium converts to nitrate. And there's more beyond that. I just excluded it for the simplicity of this discussion. So like I said, the plant root neutralizes this acidity when it uptakes nitrate. It releases a hydroxyl. And you remember I said water was pure water had equal concentrations of hydrogen and hydroxide, okay? So that's the opposite of acidity. This is alkalinity. And so those two, the hydrogen and the hydroxide, make just water. It's neutralized. But if we leave excess nitrate out there, we're leaving this hydrogen out there as well, and there's nothing to neutralize it. Some states have lime recommendations that go along with their nitrogen recommendations for corn. And I've been thinking about that, and we've kind of taken a little pressure in South Dakota through the years because of that. Why don't we include that in our nitrogen recommendation? Because, everybody has the internet now and can read, right, and look. And what that tells me is those states automatically know their farmers are applying too much nitrogen. That's what that emits to me right out of the gate, okay? If you follow SDSU's nitrogen recommendations, you got a good yield goal. It's been lowered to 1. I think Jason's here. I saw him, Jason Clark. It's 1 pound of N per bushel of yield goal. If you follow that, you still could be applying a little bit too much nitrogen. But we want to be on that side of error instead of causing a yield loss. So there's a lot that goes into a recommendation and developing that, and it's broad scale, it's not local. The best thing for you to do on your farm is do some test strips on your own. What is the best nitrogen rate for my system? Okay, your system. And you should be doing that. Because I really think most of you have the tools to do it. You just need to take the time. And when you're planting and fertilizing, doesn't necessarily happen, does it? But think of that time investment into discovering that information. It could pay you back hugely in the future. Okay? Dr. Dave Franson from NDSU is the soil fertility specialist there for years. I'll quote him. He says, all fertility is local. And he's spot on. Okay? It's the truth. We have these broad recommendations, and that's what they are. They're broad. But if you can hone in onto that recommendation on your farm, that's what you should be doing. So there's that hydroxyl plus that hydrogen neutralized into water. Okay, here's some research from the Southeast Farm where we applied different nitrogen rates and timings to corn in a corn-soybean rotation. And here's those rates, 110, 200, 400. And you can see the effect on soil pH. See what the 400 pounder did? Okay. So that proves that overuse of nitrogen fertilizers is acidifying our soils. In fact, I did a lot of the work on these plots and I got to see a lot of the data. And, you know, the next year it won't be 5. It could be 5.3, could be 5.4. I've seen that number from that plot, because we did it many years, as low as 4.4. Okay? 4.4. So too much nitrogen is not a good thing. And that, you know, when you think about that, that's the importance of soil health. That's the importance of what everybody's talking about. Increasing organic matter. Because for every 1,000 pounds of every 1% of carbon in the soil, there's 1,000 pounds of organic nitrogen. Okay? That's why it's so important to increase carbon or organic matter in your soil. Okay? You don't need as much fertilizer. Here's the lime recommendations that we have. It's based on the buffer pH, buffer index. Here's the ranges, and here's the amount of lime. Ag lime to apply with a 90% calcium carbonate equivalent or a total effectiveness of 70%. Those are big numbers. That's a costly process. It has a lot of sticker shock. Okay? And it's going on all over. There's a lot of lime going on in South Dakota. And maybe some of you in the room have done it. Okay? It is. But once you fix that or change that pH, if you've done a good job of soil sampling and a good job of applying your lime, it's done. You shouldn't have to do it for several years afterwards. I did some in 2003, and I have not had to come back to that field. But I've been practicing no-till and crop rotations and cover crops and lowering my nitrogen rate, and I've been trying to avoid it that way versus writing the big check. Okay. Here's lime being spread. What happens when you apply calcium carbonate? There's the acidity left over, right there, the hydrogen, plus the calcium carbonate. You get calcium and bicarbonate. Okay? That's how it's neutralized. And CO2 goes off right here. Turns into water and carbon dioxide. So all of you that know a lot about CO2, this is going in the direction that they don't want you to go in, isn't it? Right? That's another day, that's another topic, but think about that, okay? Okay, lime sources. There's some ag lime in pits, very good sources of ag lime. Pelletized lime is nothing more than ag lime ground up and stuck back together. There's the water treatment lime that I talked about. And then the lime water, the solution, this process, they use it to remove the hardness in the water. So that water treatment lime will have iron in it. It'll have magnesium in it. It'll have other cations. That's not going to hurt anything, okay, by applying that. And then, of course, the other lime sources. I'm going to talk a little bit about lime effectiveness. I don't think I want to dwell here a lot, but we talk about calcium carbonate equivalent. It's just how good is the lime. It's very important to have good lime if you're going to lime, so that you know that will do the job you want it to do. And so it depends about how big it is. The more finely ground lime is, the better job it will do at neutralizing acidity. Here's some work out of Iowa with different mesh sizes here. The bigger stuff, the smaller stuff, and you can see the smaller stuff. Smaller, bigger, I'm sorry, I always get that backwards. The smaller stuff's doing a better job than the bigger stuff. The bigger stuff's still neutralizing acidity, but it won't get the job done as quickly as you want it to. So here's this equation for determining how good the lime is. You know, Minnesota, Wisconsin, Iowa, all the eastern states, they have state laws regulating the sale and quality of lime because they've had all these battles, right? We don't have that in South Dakota yet. You know, I don't know if we ever will, but that's basically how it's calculated. I just wanted you to have an awareness of that. They look at all of the fractions, different sizes, and calculate that all out and look at the overall efficiency of the lime source. So we did some work in Brookings on tillage. basically look at here, conventional no-till right here. These are the soil depths. The Czech didn't get any lime. The Brookings is the water treatment lime from the plant there. And then the SuperCal is a lime from a ag lime pit. Basically, the Brookings lime did just as well as the lime from the lime pit in Iowa. You can see we started out at a 5.3 and the lime was very effective in neutralizing that acidity. Now if we look at the conventional till versus the no-till, we could neutralize acidity in no-till, just apply it on top. Okay, a lot of producers ask that question, do I have to incorporate it? How deep do I have to incorporate it? And if you've been no-tilling, you don't need to. The effect isn't as deep here. If you look at depth here, the Czech 7.36459, you got a little bit more neutralizing to that 4 to 6 layer, but I don't think it's that much to worry about. Here's Iowa State University, different sources of lime. I always get the question, is pelletized lime good? Does it work? Well, it's real lime. You're just not putting on enough. It's a product designed to go through air floating machines. Air floating machines only put up to maybe 500 pounds a pass, right? And how many passes do you want to make to get 2 ton? That's added cost, right? So basically our control pH here is in the red. See, it stays down there. That's the variability in testing, okay, and sampling. We have the powdered at a 1/2 ton. We've got the pelleted at a 1/2 ton. And we've got the pelletized at a 1/4 ton. Here, all hanging down there, didn't do nothing. Didn't do a thing. It's only the higher rates and finer grinds that have the best effect on pH. Here's South Dakota data from a number of years. Here's how we kind of get that 6.4 buffer pH here. Like these points below are responsive to lime application and phosphorus. You'll notice there's not a big difference between the no-till plots and the conventional till plots. That's corn. Here's soybeans, same story, amazingly, same story. And then let's go back in time. This is 1929 from Illinois. Lindsay there is the author. These guys are shoveling lime into a broadcast applicator, and they already knew that they needed to apply some lime in 1929. This is the first example of precision ag I've ever seen because they followed this map, that map right there. They took grid samples and they knew how to measure pH the old-fashioned way. They didn't have a hydrogen ion selective electrode plugged in electronically. There's a chemistry way to do it with color. Okay, that's an old-fashioned thing, but it's Circular 346, 1929. There's where their recommendations were. So that's the first example. And then Dr. Peck came back in a field, and he did some grid sampling and some Krieging and some fancy mathematics, came up with a pH map, and then here was his recommendations: 4 ton in the gray, leave the rest alone. And that's the important thing about liming. You do not want to blanket cover a whole field unless the field is the same. Because if you put lime on a high pH soil, you can't reverse it. You just can't reverse it. And I know that it's been done because I've talked to the folks that did that. Okay, so don't go there. So then the results here is look what happened to that low pH area. It worked. Okay, so let's talk about the other problem. Why I got asked to come. What about increasing? Everybody wants to increase. What about lowering pH? What about lowering pH? This is Clemson University's recommendations for applications of elemental sulfur right here, depending upon soil pH and that you want and the pH that you have in the soil. You can see that the rate of elemental sulfur goes up as the more acidification you want to do. So elemental sulfur interacts with soil biology and acid is produced. Okay, kind of making your own battery acid in the soil, if you will. H2SO4, sulfuric acid. We did some work on this very thing in South Dakota. I worked for Jim and Ron here. This is out of 1996. We put on these rates of elemental sulfur. Yes, that's 8,000 pounds of elemental sulfur in small plots. These are different years where we measured the pH. After we put that on, you can see the pH in this field was just under 8. 2,000 pounds did decrease it, but it took a little bit of time. See here, by about 1994, we were down to 6.7, but look what happened in 1995. You can see that power better with the 4,000 pound, it kept it lower, and then the 8,000 pound kept it even lower. So the alkalinity is coming back. Why is that? Could be. Not at this site. This is a very well-drained site. Anybody else? There's a heck of a lot of it there. It would take hundreds of years. Not saying I'm not correcting you, but thank you. Keep them coming. This is how we learn. That could be. This is a tilt site. Yep. You're really close to the answer I'm looking for. Free calcium carbonate. Free calcium carbonate in the soil. Some soils, you can, if you get a little muriatic acid at the hardware store, be careful. It's not going to burn your fingers off, but just be careful. Don't get in your eyes. You can buy it. And just put it in a little dropper bottle. You can walk around your field and just drop a little on the soil and see if it fizzes. If it fizzes, you have free calcium carbonate in the soil. They're microscopic, small concretions of calcium carbonate. You can't see them like you can in the soil profile that I showed you. You could see the larger concretions, right? You can't see these. And that's what's causing this pH to creep back up. So this comes about because you would not believe how many questions of homeowners have called and said, I want to grow blueberries so bad. How do I do that? Well, you go through this lingo, right? I had a guy who bought a 50-gallon drum of battery acid. And I said, you better be careful for starters, okay? And he was dead determined to grow blueberries, okay? I'm going to grow blueberries. And you go down this road talking about calcium carbonate, and, you know, it gets technical, because it is. It just flat out is technical. Okay, look what happened to soil pH or soil phosphorus in these plots.
Well, now you're leaving us hanging. Was he able to grow blueberries?
You know, very few of those people call me back. Because my message is, go ahead and try, but I don't think you're going to be successful. Now I hear there's a blueberry that's more adapted to higher pHs. I have heard that. We should ask Robin, but anyway, look what happens to soil phosphorus here as we decrease pH. Remember the 8,000 pound rate? Look at what those numbers. No phosphorus added. None. Here we have a very high pH, right? That 7, 7, 7, 7, 8. And here we have like 6 something. Okay? Remember that chart I showed you about all the elements and the pH? Here it is. Real life. Okay? I better get going. So here's the sulfur rate by depth and the amount we put on. We know that the deeper in the soil profile, the less effective that was. I just put that in there for that. And now we have 3 sites, Brookings, Yankton, and 2 at Yankton, because Gurney's, remember Gurney's? Remember that? They were interested in this too. How come we can't grow blueberries, right? So they put out 2 sites, put up various rates of elemental sulfur. A couple sites had 8,000, one had 16,000. Okay? We know you can't afford to do that, but we just have to see what happens. Here's the free calcium carbonate percent in these soils. Okay? Right there. You can see what that 16,000 did, right? 3.8. It took it way too far. Way too far. But that's the key. If you've got anything, I don't have enough data to say what's the magical number of calcium carbonate before you can do it or not do it. But if you're above 1, don't even think about it. If you're at 0.5%, yeah, you can probably be successful. So that's the first thing I say, get that test done, and then call me back. Okay, so what about soil health practices? What y'all came for, okay? Rotations, what do? They reduce end use, provide opportunities for cover crops and grazing that will help increase pH. Bring those alkaline cations to the surface, right? Those forages contain calcium, magnesium, potassium, goes through the cow, goes back on the land. Okay, that's what that does. Cover crops help convert nitrate from inorganic to organic forms. Remember I said the OH ion that's released? Well, the cover crops do that too. So they're neutralizing acidity as they're taking up residual nitrate. Perennials convert inorganic alkaline minerals, calcium and magnesium, to organic forms to offset acidity. Water use increases, which can bring alkaline minerals near the surface. Dr. Dwayne Beck's biggest fear about our agriculture is that acidification of soil will take over, okay? And we need to put perennials back in our systems for that to happen. And he's researching it at the farm. He has a rotation with a perennial in it, okay? Grazing livestock can help convert carbon stocks to more humus that can hold more alkaline minerals. The cation exchange capacity increases as the organic matter goes up in the soil. Okay? And David Kruger reminded me I forgot one here. Ground cover. Keeping the ground covered slows evaporation and slows the formation of saline and sodic soils, which have a high pH. Okay? Those are the soil health principles. Right there. Okay, in summary, soil pH is very important. Soil health indicator, it is. There's 17 of them, NRCS, folks. How many soil health indicators are there? There's biological, chemical, and physical. Soil pH is one of the chemical ones, right? Okay, if you don't have the right pH, you're not going to have good soil health. Our soils are naturally very alkaline. Nitrogen applications above yield levels have decreased soil pH. Lime is an effective way to help increase pH. It does work. It does work. Reducing the soil pH is very difficult and could be cost prohibitive, especially if the calcium carbonate content is too high. That's statement 6 there as well. But 7 is key. And that's why I've quit really worrying about liming on my farm. If you focus on those principles, it's going to take care of itself. And especially if you lower that nitrogen application rate. That's the driver. That's the driver. So with that, I'm done, and thank you for your time, and hope you have a few questions, maybe not. Yep.
You mentioned you don't know what the safe level of calcium is. Are you familiar with the Kinsey-Albrecht model?
I sure am.
And it's that 60-80 rule with low mag, high calcium, pretty economically soils, all that fun stuff.
Well, what I would challenge you to do is, if you're farming, take soil samples and send some to a traditional lab and some to his lab. And get back those results and follow his recommendations to the T. And then call me back. What generally happens, I had a very influential landowner do this on several of his fields that he owns. And his response about the Kinsey recommendations were, I can't believe I have to apply all this stuff. And the cost is astronomical sometimes. Sometimes. Not always. So I just beat up Kinsey, right? Because every time he comes to South Dakota, I get these calls. And that's okay. That's my job. But, you know, I've had other farmers talk about calcium and magnesium ratios. And I say, well, do a strip. Put a strip out. See for yourself. I've had a few of them come back to me and say, not a thing's happened. Not a thing happened. We go by the sufficiency level and the university level because our soils have high amounts of the plant essential nutrients, calcium, magnesium. We have high cation exchange capacity levels. Where the Kinsey method comes in is where you have CECs, now don't quote me 100%, but very low, 2, 3, 4. Ours are 15 and above. Granted, there are some soils in South Dakota that may get down in the 5 to 10 range, the sandy soils. And someone's going to go out on a sugar sand slope and take a sample and say, Anthony, I found a 3. You know. But that's the reason. Because we're dealing with such big amounts, the base saturation cation approach doesn't work. Dr. Clark, Jason's not in the room, right? Is he out there? No, okay. He has tested the base cation for potassium and put out rates of potassium to get to that 2% or 3% or 4% potassium in the soil. And all he's seen is yield reductions by going too much. Okay? And he has said don't put on any more than 200 pounds of potassium a year. Okay? If you need to raise it, just stop there. Because he's seen that over and over and over. Great question. Thank you. Anybody else? Yes. Oops, sorry. I'll come back. Yep.
How have you seen heavy rates of manure affect pH overall?
Most manures have a liming effect on the soil. So the pHs go up. Is it drastic? No. It's a nice, slow incline. Now, some hog manures, I think the sow barns are a different story. Okay? I think it's more acidic. But those farms are going to be offset by finishers and, you know what I mean? It'll all work out in the end if they do it right. Yep.
What is the ideal pH?
Well, you'd like to be in that range 6 to 7.4, 7.5. Yeah, you'd like to be. There's a lot of soils that are above 7.5 that, quite frankly, you can't do much about. They're just going to be that way. Yep. David.
So if over nitrogen application lowers pH, does it do the same thing in a high pH soil?
Not as fast as you want it to.
I'm not
I know.
encouraging people to do that.
No.
It's just a question.
It's a good question. Can I put 2-3 tons of nitrogen out there and get the effect? Nope, it won't be that fast. It will have a acidification effect, but it's not going to be you're not going to be happy with it. Oh, that's a great question too. Okay. Yes.
Do different forms of nitrogen affect its ability to acidify that?
Yes.
So if we're looking at like urea versus some type of solid versus liquid nitrogen?
If plants take up ammonium, plants can take up ammonium and nitrate. If plants take up ammonium, there's more acidification of the soil than there is with nitrate. Because the plants are offsetting the acidification with that OH group, you remember I talked about? Okay, so yeah, so that's your forms of fertilizer nitrogen. I'm not saying don't use them because nitrification's dynamic. Soil biology is working on that all the time, right? You can't really control how much ammonium's in the soil at any one time. The biology controls it, right? Yeah. So, yes.
If you have a low pH and your recommendation is 5 ton, are you better off doing 5 ton at once or 2.5 each year?
If you've done a really good job of sampling, okay, and the lab is really good, get it done.
Would that be the same case in a no-till situation? That lawyers are half as much twice as often.
Yeah. Well, we can go back. You said 5 tons. So where is that on our
Which is a lot.
which is a lot. That's a high rate. That doesn't happen. That's not even on our chart. See, we're at 3.5.
Next Gen Ag will do a variable rate application, and it's typically like a 3-year solubility. If you put it all on 1 year, you're not gonna see the results until the end of year 3, typically with lime.
If the lime is right, you will.
Instantaneous.
It'll change it. Yeah, but it's got to be fine. Remember my talk about the grade, and yeah, it can do it.
And that water treatment lime is some of the best stuff you can get your hands on.
It's good. I mean, it's not as good as really good ag lime. It's not, but hey, it's what you got. It's local. You know, you're going to double transportation or triple transportation costs? No, you're not going to do that. You're going to use what's local. Yeah. Another reason maybe for changing it incrementally is just cost. Just cost. You know, it bites. It'll bite you pretty hard. It's like an investment in the soil. You don't try to pay for it in 1 year. You're going to pay for it over 10 years. Right? But we probably shouldn't have got there in the first place. I hate to be the stinger, right? But hey, there's problems and they need to be fixed. So, yeah. Yes, sir.
How much of an effect does the moisture at the current year, if you see high rainfalls and pHs drop just due to leaching, do they recover after a few dry years, or what do you think?
You'll see variability, not great differences from year to year in sampling. Some of that's just sampling randomness, right? We call that error, okay? There's differences in where you took the sample, how deep you took the sample. You got those differences from year to year. But remember the soil colloid, that hydrogen on the colloid is equal to the hydrogen in solution. And that isn't going to change. That's being held there statically. So you don't leach out acidity.
You leach out the calcium, right?
Well, what happens is when you offset, now we're getting pretty, this is going to go, oh shoot. Okay, let's just look at this one. We've got this hydrogen here. Let's say this is acidic soil and there's a lot more hydrogen there. You put the lime on, you interact with the hydrogen in solution, okay? And then you've got a bunch of calcium there. You've flooded the system with calcium. That's kicking off even more hydrogen because the calcium wants to equilibrate, right? Same amount on the colloid, same amount in solution. So then even more lime is reacting with even more acidity. That's the process. And yes, then we are getting movement of some things. Because it can only hold so much. Anybody else? Great questions.